So now we understand this idea of orthogonal complements as two vector sets in which every vector in one set is orthogonal to every vector in the other set and vice versa. So we have that idea in mind, and we've already defined the four fundamental subspaces as the column space, the null space, the row space, and the left null space of a matrix. We kind of want to bring those two ideas together into one video here. And the reason is because, and we'll draw a picture to make this a little easier for us to see, by definition, we actually know that the row space and the null space of a matrix are orthogonal complements of each other. And often we like to draw the two spaces like this because these two spaces are these two rectangles are kind of orthogonal to one another. They sort of have this 90-degree angle relationship between them. So we'll often illustrate the spaces this way. But if we say that this is the row space, so we'll call this rectangle up here the row space, and we'll call this the null space. So these two have an orthogonal relationship to one another. They are orthogonal complements of each other. So one way that we could write that, we could say that the null space of A is equal to the orthogonal complement of the row space. So we write the row space as the column space of A transpose, and then we want to take the orthogonal complement of this, so we add this perpendicular symbol. So the null space is equal to the orthogonal complement of the row space, or we could do it the opposite way. We could say the orthogonal complement of the null space is equal to the row space, which is the column space of A transpose. In other words, in the same way that we had the spaces V and V perp, we have these spaces, the null space and the orthogonal complement of the row space, or the orthogonal complement of the null space and the row space. So we have these equations here that relate the row space and the null space. And then similarly, we have the same orthogonal relationship between the column space and the left null space. So if we call this up here the column space is the orthogonal complement of the left null space, and the left null space is the orthogonal complement of the column space. So if we wanted to write that in terms of an equation, we could say that the column space of A, is equal to the orthogonal complement of the left null space. So we'll say the null space of A transpose, that is the left null space, and so its orthogonal complement looks like this. Or, equivalently, we could say the null space of A transpose, which is the left null space, is equal to the orthogonal complement of the column space, which looks like this. And if we want to call these up here, let's say this is the column space, this is the left null space, the null space of A transpose, this is the null space, and this is the row space, which is the column space of A transpose. The other thing that we know as a rule is that when we have a space and its orthogonal complement, their dimension, the dimension of each of those subspaces, will always sum to the space that contains them. So let's say that we have V and V perp, and they're both contained in Rn space. So V and V perp are both in Rn space. What we know then is that the dimension of V plus the dimension of V perp, because they are orthogonal complements to each other, that's going to be equal to n, the dimension of the space in which they're contained. In other words, let's say we're in R2. If the dimension of V is 1, that tells us that V is a line. Well, 2 minus 1 is 1, so we know that V perp, its dimension also has to be 1. It also has to be a line. Remember that dimension is just the number of vectors needed to form a basis for the subspace. So we're saying that the number of basis vectors that we need to form the basis for V, plus the number of vectors that we need to form the basis for V perp, those two things have to sum to the space that contains V and V perp. And so in the same way, of course, because we've defined these fundamental subspaces as orthogonal complements of one another, that means the dimension of the null space plus the dimension of the row space always has to be equal to the space in which these two are contained. And then same here, the dimension of the column space plus the dimension of the left null space they have to sum to the space in which they're both contained. And that's why before, when we built out our diagram, when we first talked about the 4 fundamental subspaces, we said that if the row space and the null space are both in Rn space, we know that the dimension of the row space is always R, the rank of the original matrix A, because that's given by the number of pivot columns in the original matrix A, or the number of pivot rows in the transpose matrix A transpose. So our dimension for the row space is always going to be R. Well, that means that by definition, the dimension of the null space, so the dimension of the null space has to be equal to n minus R, because when I take this value, I have to be able to add it to R to get n. So n minus R plus R gives me n. That's why the dimension of the null space has to be n minus R. And then same thing here, we define the column space and the left null space in Rm space. We know the dimension of the column space is always the rank R, which means the dimension of the left null space always has to be equal to m minus R, because I have to be able to sum m minus R and R to get m. So by definition, that has to be m minus R. So in general, this is just a super helpful diagram for remembering the spaces, the dimensions, and which spaces are orthogonal complements of each other, so we can kind of define this orthogonal complement relationship. We also want to say, as the last thing about this diagram, that when we think about these spaces geometrically, we're saying that every vector that's contained in the row space has to be orthogonal to every vector that's contained in the null space. Well, by definition then, that means that any of the vectors that are in the row space cannot also be in the null space, because if you have an identical vector in both spaces, that vector, of course, is not going to be orthogonal to itself, which means that you'll never have any overlap at all between the row space and the null space. They'll be entirely different sets of vectors, except for the 0 vector. The 0 vector, technically, is contained here at the intersection of the 2 spaces, so we'll just put here the 0 vector. The 0 vector is contained in the row space. It's also contained in the null space. And so that is the only overlap between the 2 spaces. Otherwise, any other vector that's contained in the null space will never exist in the row space, and vice versa. And the same thing goes for the column space and the left null space. The only overlap whatsoever is the 0 vector. The 0 vector is contained in both spaces. All other vectors have to exist only in the left null space or only in the column space. You can't have any other vector that exists in both spaces. So just to give you an idea of how this plays out in terms of an example, let's look at a matrix. Let's say that maybe we have the matrix A, and maybe it's a 3x4 matrix. So maybe it's 1, 0, 0, 2, and then -1, 1, 2, 0. And then we'll say 2, 0, -1, and 1. So we have a 3x4 matrix, and what we want to do is find the dimension of all of our spaces. Well, we can do that really quickly as soon as we have the matrix in reduced row echelon form. So let's go ahead and put it in reduced row echelon form. We'll do that first by keeping our first row, 1, 0, 0, 2. We'll add the first and second rows together to replace the second row. So we'll get 1 plus a -1 is 0, 0 plus 1 is 1, 0 and 2 is 2, 2 and 0 is 2. And then for the third row, we'll take away 2 of the first row from the third row. So we'll get 2 minus 2 times 1 is 0, 0 minus 2 times 0 is 0, -1 minus 2 times 0 is a -1, and 1 minus 2 times 2 is 1 minus 4, or -3. Then we'll just multiply through the third row by a -1, so we'll leave the first 2 rows the same. And then in the third row, we'll get 0, 0, +1, and +3 when we multiply through by -1. Then we'll take away 2 of the third row from the second row, so 1, 0, 0, 2. Then we'll say 0 minus 2 times 0 is 0, 1 minus 2 times 0 is 1, 2 minus 2 times 1 is 2 minus 2, or 0, 2 minus 2 times 3 is 2 minus 6, or -4, and then 0, 0, 1, 3. And now we have our matrix in reduced row echelon form. What we see is that we have 3 pivot columns and therefore 3 pivot variables. We've got a pivot column, a pivot column, and a pivot column. And then we also have here a free column. Remember that the rank R and the dimension of both the column space and the row space is given by the number of pivot variables, given by the number of pivot columns in the original matrix. So right away, if we want the dimensions of all of our spaces, we can see that if we make a table here, we'll say this is the space, and we'll say this is the dimension. So for the column space, the dimension is going to be 1, 2, 3 pivot columns. So the rank is 3, the dimension of the column space is 3. We know also that the dimension of the row space is 3. So the column space of A transpose, the row space, its dimension is also 3. Then we know that A is an m by n matrix, right? It's an m rows by n columns matrix. So m is 3 rows, n is 4 columns. So when we're talking about the null space and the left null space, the null space of A transpose, the dimension of the null space is going to be n minus r. Well, that's 4 minus 3, or 1. And then the dimension of the left null space is going to be m minus r, or 3 minus 3, and we get 0. We could also put in here that the column space and the left null space are in Rm space. So the column space is in R3 space, and the left null space is in R3 space. And then the null space and the row space are both in Rn space. Well, n is 4. These are both in R4. We could have also found those spaces by summing the dimensions. So if we take the dimensions of the column space and the left null space, we could say 3 plus 0 is 3. That means the column space and the left null space must be in R3. And for the null space and the row space, which are orthogonal complements of each other, we could take the dimensions 1 and 3, sum them to get 4. We know these two spaces are contained in R4. Or we could have gotten it from the rows and columns of A like we did before. So either way works. But then if we want to actually describe each of these spaces, we're told that the column space has 3 dimensions, which means we need 3 vectors in order to form the basis for the column space. And the column space is contained in R3. So because we need 3 vectors, that means the column space is just all of R3. If we have 3 vectors in R3, that means we're going to be spanning all of R3 space. So the column space of A is all of R3 space. The null space of A, anything with 1 dimension, is a line. So the null space of A is a line in R4. To span the row space, we need 3 vectors in R4. So 3 vectors in R4 is something that's really difficult for us to visualize, but basically it's a plane, it's some kind of a surface, a 3-dimensional space that's contained inside of R4. So it doesn't span all of R4. We would need 4 vectors to span all of R4, but it's a 3-dimensional surface contained within R4. And then the left null space, the null space of the transpose, because its dimension is 0, it's just the 0 vector, and it's the 0 vector in R3. So if we were going to set this up before we even find each of these spaces, we could say that the column space of A is given by the span. We know that we need 3 vectors in R3. So really we could sort of build out a template like this for ourselves. We have 3 vectors in R3, and we know we need 1, 2, 3 components in each one since they are 3-dimensional vectors. So our column space is going to look something like this. The null space is going to be 1 vector in R4. So we could say the span of just this single 4-dimensional vector, 1, 2, 3, 4, in R4. We know that the row space, so the column space of A transpose, is going to be 3 vectors in R4. So if we sketch that out, we would have 1, 2, and 3 vectors in R4 space. So 1, 2, 3, 4. They're each going to have 4 components. And then the null space of A transpose, the left null space, is going to be just the 0 vector in R3. So we could just write that as 0, 0, 0. That's the 0 vector in R3. So hopefully you're starting to see how these 4 fundamental subspaces are related to each other and how their properties make sense together. This is a really useful tool, this process we used, when you're going about finding these 4 fundamental subspaces, because you can take your original matrix, quickly put it into reduced row echelon form, and once you have that, you know the dimension of each of the spaces, you know the spaces in which they're contained, and you can therefore set up this template like we did so that you know exactly what you're looking for. So as you're going through the process of actually finding the column space, you know that you're looking for 3 vectors in 3-dimensional space. When you go about finding the null space of the matrix, you know you're looking for 1 vector in 4-dimensional space, 1 vector with 4 components. So you can kind of have this template to work from just by doing this quick little analysis up front, and that'll help you double check to make sure that you're getting the right basis for each of the 4 fundamental subspaces.